Ah, yes. Yeah, so anything that you can solve with recursion, you can also solve with a loop. Anything that you can solve with a loop, you can also solve with recursion. But usually one of the ways is more elegant. When you're writing a recursive function, what do you need? You need a base case. Why do you need a base case? You'll enter an infinite loop, your computer will break, the universe will like implode upon itself. Yes. Okay, so what does that mean to have a base case? A terminating condition. There has to be, so when you write, so let's just go into this, let's see. When you write a function, so let's do factorial. One of the articles talked about factorial, right? Yeah, so does it, can somebody tell me what factorial is? What's factorial 7? So if I do, so 7 factorial also equals, or this also equals 5 times 4 factorial, which is really useful for recursion. This is recursive because it's like, so this is how I like to think about recursion sometimes. It's, if I only knew how to do 4 factorial, I could tell you 5 factorial. And how do you do 4 factorial? Well, you just use the same function on 4. Another teacher I worked with sometimes called this faith-based programming, right? Because you're like, okay, well, fine. 5 factorial is just 5 times whatever 4 factorial is. So I'm just going to feed 4 back into my function and hope that things work out, right? So, okay, so we have to have a base case and a recursive case. There has to be some sort of condition where we don't recurse. We can talk about the recursive case first because here it is. So how would that look in code? Like that? Ah, yes, that's important. Otherwise, it would just do 5 times 4 and nothing, and that would be it, right? We need to, the recursive case needs to call calculate factorial on n minus 1. What's our base case? When are we done? What do we do?
Return. What about cases in the less than 2?
Okay, you happy?
Is that also base case?
It is another base case. Anything where you don't actually recurse is a base case. Technically, the 0 factorial is equal to 1. That is part of the definition of factorial.
Because I see that Code Academy, they separate base case and termination case. So, yeah, because, and so that -0, they call it that termination case at this point.
Okay, because I guess this might be called. Okay, I'll entertain Code Academy's terminology here. The difference is this one might get called recursively. This one will never get called recursively. This is really just like kicking somebody in the ass and being like, get out of here, right? Whereas this one could get called if somebody did calculate factorial on 0 or 1. Or it could get called recursively. So let's put this in my favorite. How'd that get there? Oh, I didn't show you one of the jokes. There are a lot of recursion jokes, but if I search for recursion in Google, says, "Did you mean recursion?" And then you yeah. Okay. So yeah, that's there are a lot of recursion jokes, but that's a nice one. Okay. So let's go to the JavaScript tutor and let's put this code in here. And then let's call calculate factorial on 4. Thank you. Okay, so let's run this. Okay, so here, all right, so now it's just gonna go, I'm gonna make this a little bit smaller. Oh, that's gonna be really hard to read. You guys cool with that? Okay, all right, so N. So first, the first call, so right now, oh, and I like to use penguins for recursion because, so right now we did our first call is with n equals 4, right? And so it goes through, n is not less than 0, n is not less than or equal to 1. So now what we're gonna do is we're gonna pop open another penguin and we're gonna call it on n equals 3. So now we have 2 calls on the stack. We've got n equals 4 and n equals 3. For n equals 3, it's not less than 0, it's not less than or equal to 1, so we pop another penguin, right? And now we call it on n equals 2. Now, n equals 2, not less than 0, not less than or equal to 1. So now we're going to call it on n equals 1. So now we have 4 calls on the stack. We have not completed for n equals 4. We have 4 calls on the stack. We've hit our base case. N is less than or equal to 1. So we are actually going to return 1. And we are back in our n equals 2 case. Do you see that? Then we return 2 because that's the 1 that we got back from n equals 1 times 2, which is what n is now. And we close that function. So now the only functions we have are n equals 4 and n equals 3. The n equals 2 returned 2. We multiply that by the 3 to return 6. We close the n equals 3. And then we take that 6, multiply it by the 4 that n is now currently equal to, and we're done.
So it takes everything onto step and then does the multiplication.
Yes, this right now we are doing, so you can think about recursion as kind of digging the hole, and you can either do the work on the way down or on the way back up. This one is doing the work on the way back up.
How would we do it on the way down?
We can't really do it on the way down for this problem, although that's tail recursion. To do it on the way down for this problem would mean, and we're going to deal with this with Fibonacci, would mean that we would have to do the numbers in reverse. We would have to start in when n equals 4,
Yeah.
we would actually be working with the number 1. And then when n equals 3, we would be working with the number 2. When, you know, so it's like doing things in the reverse order for this particular problem. There are some problems where it makes sense to do the work on the way down, and some problems where it's more contrived. Okay, cool. How did people do with Fibonacci? Were people able to write a function for it? No.
No.
You got part of the way there recursively. Okay, so tell us what you got, James. We're all friends here.
So the first thing, and this is where I was writing, the first thing I did was declare an array outside of the function. And I needed a way to value.
Like this?
Yes.
Okay.
And then, so the function took the n and then 8. And I said let result equals b plus a. And then after that line, b equals a. A equals result. Value dot push result. And then if value dot length minus 1 is greater than or equal to n, return result. Else calculate fib with n. So I got it to the point where it was like building the array. I wanted to on sequence, but then
Okay, I'm going to, oh, right, because the value, this was on the outside. Okay, got it. I am going to leave that because that's actually, that is the way to do it faster, but it's also more complicated than I want to do right now. So, yeah, okay. So right now, I believe that they don't ask you for the array, right? They just want you to give it the Fibonacci number. Right? So if you do Fibonacci n, it just returns the nth Fibonacci number. You don't actually have to do the array. Let's talk about that in a minute. So, okay, so here, so you guys understand what Fibonacci is? Okay, so Fibonacci n, can you give me a formula for Fibonacci n? Yeah, so if I do, I'm going to call this calculate fib slow because it's going to be slow. But so my recursive case is return calculate fib slow of n minus 1, right? If I knew what fib of n minus 1 was and what fib of n minus 2 was, I could just add them together and get this. Right? Again, it's this whole like faith-based programming, this whole like, fine, whatever. If I know what the former two are, I add them together and I get what I need. Okay. What are my base cases or my base case here? 0 and 1, I'm just going to return 1. Is this okay? Is this a 1 index and not a 0 index? Whatever. Okay, that's fine. All right, so yeah, well, if we're doing 1 index, then I want index 1 and index 2. If we're doing 1 index, whatever. I'll just put a note. Okay, so okay, let's try it. What should it give us? 2, because we should be this, right? Cool. Let's try. Okay, 1, 2, 3, 4, 5, 6. 6 should give us 8, right? Awesome. Who said this was slow? Okay. All right, so 7 should give us 13. Great. You want me to try 77? Why is it taking so long? And creating that stack 77 times. My computer is pretty smart, and it can creating that stack 77 times. No problem. It is not creating that stack 77 times. I think it's creating it 77 factorial times. I'm not sure. Okay. Let's look and see. 10 minutes for 79. Did you get 77? Did you get 77 back?
No, I just tried 79.
Okay, you just yeah, because like 77 was like too low for you. Okay. So let's just start with, let's say 6. So if we do, I'm just going to say fib of 6, even though this is generally not a good function name. A good function name is verby. It tells you what the function does. But I'm just going to do this for now. So fib of 6. Sorry for you people who are on the recording. Very sorry. Fib of 6 is going to be fib. You're going to have to calculate fib of 5 and fib of 4, right? That's what it's going to do. Fib of 5 is going to calculate fib of 4. This is pretty inefficient because I'm calculating fib of 4 twice, and fib of 3. Fib of 4 is going to calculate fib of 3, fib of 2. Oh no, fib of 2 is a base case. Okay, so fib of 2 is a base case. All right, so fib of 3. All right, back to fib of 4. Look at how many calls I did just for 6. Mm-hmm. And if I did 7, would look like this, and then fib of 5, right? Yeah, that's why I called this a naive way to calculate Fibonacci. It is very logical and very, like, if you're thinking about recursion, this is what you do. Is 77 back yet? No. But it is horribly, horribly inefficient.
What was the
2 times.
Oh, is it 2 to the n?
Yeah.
We call this exponential.
Oh, yeah.
Much, much worse than n squared, right?
Yeah.
So 2 to the 77. How do you raise to a power in JavaScript? Do you know? Is it double star? Okay, so 2 to the 77 is a 1 with 23 zeros after it.
Wow.
Yeah. So, right. So, of course, that's going to be slow. How can we make it faster? What are you thinking with that melodious suggestion? So what Steph is suggesting is called memoization, which always makes me think of like my niece trying to say memorization, memoization. Memoization. So this means all right, so what I can do is I can say, I can have like a helper function. And I can say, so now I can say, so I'm now just making a history of everything I've calculated. And I'm making it an object. And now I'll say, calculate now I'm actually going to return calculate fib what do I want to say with memo. And so I'm also going to define sort of in here, like I have an inner function and I'm going to say const calculate fib with memo. And that's going to take both an n and it's going to take the fib history. And then I'll run that on n, and let's see. Sorry, so I'm clearly I didn't like practice this beforehand. I can't remember whether actually I don't know. You can get into trouble doing this because objects are mutable. Okay, let's just try that for now. So what I'm doing now is I'm basically saying if it's called without a second argument, just make the second argument by default be an empty object. Let's try this. So if we can have the same base case, no problem there. And now we'll say next to last equals. So now I'm going to get the number before, and I'm going to see if it's already been calculated. Okay. So next to last is going to equal calculate. It's either going to equal this fib history. So I actually haven't been very clear about what I'm doing here. I'm going to store any answers that I've already calculated in here. So I can look them up in here rather than having to calculate them over and over and over again. So let's actually, let's forget about the fib history for a minute. So next to last equals calculate fib memo n minus 1, fine. And then next to last is n minus 2. But in this case, and I'm going to return next to last plus next to, okay. So far, this is actually identical to this up here. I haven't made any changes, right? I've just separated these out. This is going to be equally slow. Celeste, how's 79 doing over there? Okay, 20 minutes. Okay. So, okay. But now what I'm going to do, I'm going to make two differences. The first thing I'm going to do is I am going to add this number that I got. I'm going to add it to my history. Okay, so now I am taking it and I'm storing that result in the history. And the other thing I'm going to do is before I just go ahead and calculate it, I'm going to check to see if it's in the history first. So before I calculate it, I'm just checking to see whether I've calculated it before. How's that sitting with people? All right, so let's try this one. Good. Okay. Let's do it on, was 7 supposed to be 13? Okay, what do you guys think? It's still having to go through all of those steps. Yeah, but the fact is it is making a ton of function calls. It's not having actually, all right, let's actually see what's going on here. So let's oh, I didn't okay, I didn't include fib history because you have to include it every time. So I was just like making it an empty array. Okay, like yeah, that was not exactly what I wanted. Okay, so let's try that one more time. You guys understand what the problem was? I wasn't actually passing along to future calls all of that memory. I was just every time just starting with an empty object, which is exactly the same as before. So again. So now let's make sure that 1, 2, 7, 77. Ah, better. Memoization. That's one way to do it. Another way to do it is with tail recursion. And tail recursion is, instead of starting at 7 and trying to like calculate everything before it, start at 1. Why not, right? And then if we start at 1, so even though we're doing fib of 7, we're not actually going to do this whole like find fib of 6 and find fib of 5. We're going to say, I know you gave me 7, but what I really want to do is start with, I don't want to go from 7 down to 1. I want to go from 1 up to 7. So it's like, okay, great. You gave me 7, whatever. I'm going to return 1, 1. And then the next time you give me 6, okay, fine. I'm going to return, so I'm going to return, I actually don't think that I had to understand this one up to explain it. I'm going to return 2, right? And so, but you have to, when you do this, you have to tell it how many you have left, right? Every time. I can't just do fib of 7 equals, fib of 1 plus fib of 6. That doesn't work, right? Instead, what I have to do is I have to tell you what were the previous 2 numbers. I can say fib of 7, where the previous 2 numbers, I didn't study this well enough before trying to teach it to you, I'm sorry. Where the previous 2 numbers are, like I know that I'm doing fib of 7 and I'm looking at the previous 2 numbers. Let's look at somebody else's solution and parse it rather than me trying to recreate it from scratch, because clearly I am not prepared to do that right now. My apologies. Spent too much time texting while you were working rather than studying this. So Fibonacci, recursion, fast. Just do that and look at that. We are not the only people who are looking to do fast Fibonacci recursion. This is the that naive one. Still going on 79. Okay. How many minutes now? 25 minutes. Okay. This is the tail recursive one. And it does get optimized. Oh, but you were saying that maybe JavaScript doesn't optimize tail recursion? Okay. Okay, interesting. Okay. So this one here now, instead, it really is like building. Okay, all right. So that's totally tail recursion. I think there's one down here that's more building it up rather than building it down. But if JavaScript actually doesn't do tail recursion, then we're screwed anyway. This one down here might be doing like a building it up rather than building it down, which you could do. You're basically going to turn it into a loop rather than recursive. Just forget I mentioned tail recursion and look at the memoization. Hooray! Okay. So, right. The memoization worked great for us. And
O of n, right?
yeah, what is the how many, yeah, what is the runtime of our memoized? Why do you say that?
Doesn't it? It depends. It has to call n times number of. It calls itself n times. It's like the number, the value that it gets in the first function. It has to call that function the number of times. It calls itself that number of.
Let's actually see what happens. Let's see what happens in the memoized version. Okay, so let's do 6 like we did before. So if we do fib of 6, it is going to calculate next to last. So it is going to do fib of 5. And the way it actually works, and this is where that visualizer comes in really handy, it'll do fib of 5, and it'll do fib of 5 before it even starts doing fib of 4. It'll complete fib of 5. So then fib of 5 we'll call fib of 4, because we're now on another penguin. It'll call fib of 3, it'll call fib of 2, it'll call fib of 1. Oh no, fib of 2, sorry, we'll come back. Fib of 2 will come back. Okay, and then, okay, so then that comes back, that comes back, that comes back, that comes back. And now our object has 2, 3, no, sorry. This comes back, and then, so fib of 3 then calls fib of 1. That gets put into our object. Okay, then fib of 3 returns. So now our object, let's actually put what's in our object. So now our object has 1, it has 2, it has 3. Fib of 4 is going to be fib of 3 and fib of 2. But now because 2 is in our object, it doesn't have to actually branch. It is because we did it here. Oh, I see. Yeah, because when we got down to fib of 3, this one actually returned, and we started to calculate this one here. This one returned because fib history of n-1 was fib history of 2, which just returns.
So then when is it getting put in our?
Oh, that's Celeste. Okay. Okay, you happy? So in that case, actually, if I do that, we don't even need this, right? I don't need a base case because there are options for it not, like this right here is my base case if it's already in the, if it's already in my memory object. Okay. So I actually never even end up calling fib 2 and fib 1 in this version. So 1 and 2 are in there, 3 is in there, 2 is in there, fine. Now 4 is in there, and it's plus fib 3, which is in there, so I don't end up recursing. Now do fib 4. Now I do end up calling all of these. No, that's not true. I don't call them if it's actually in, if it's in the history, I don't call them. So I take it back. So there's no branching here because 3 is already in here. And there's no branching here because 4 is already in there. So it is O of n. I really just go through n times. I'm not making calls. I'm not making an additional call if it's already in my memoized history here. That was such a satisfied little smile, Alex. That was wonderful. Yeah.
I'm reading here and it says, and maybe this is something, it dramatically decreases the time complexity to 2n, which will resolve to linear time since 2 is constant. That's the same of O of n, right?
Yeah.
Okay.
I do have to make a I do have to like do something here. I have to look up something in an object, but that's constant time. And so and you know, if I do that twice, that's, you know. Okay, recursion. These are simple recursion problems. If you open Cracking the Coding interview, you will get complicated recursion problems. Also, when we start talking about sorting, when is sorting? I think we do trees, graphs, and then sorting. Sorting is one of my favorites. We're gonna, the best sorting algorithms are recursive.
The best of the funnest.
The ones with the best runtime.
Oh.
The funnest.
How can they be wasting on time?
Come back in 3 weeks. So yeah, in general, when you're deciding whether or not to use recursion to solve a problem, there are two kind of ways that, you know, indications that recursion is a good way to solve a problem. One is the sort of factorial way, or the Fibonacci way, where the answer is so closely related to a smaller version of the problem, right? Where the answer is, you know, just you do a small piece of work and then you do a smaller version of the problem. Or in this case, two smaller versions of the problem. So that's one way to know that it's a recursive problem. But you know, realistically, the problems that you're going to get, the way you're going to know that they're recursive problems are if you see them branching out into trees. And here's what I mean. So a classic recursion problem is like, how many ways are there to make change for 79 cents, right? And the idea is, okay, so I can, that branches out into trees. I can start with a penny, with a nickel, with a dime, or with a quarter. If I start with a penny, then from there, I can either, so now I'm talking about making a change for 78 cents. And for 78 cents, I can do it with a penny, a nickel, a dime, or a quarter. And now if I choose the penny, I'm talking about making change for 77 cents, right? If I choose the nickel, I'm talking about making change for 73 cents. So for example, if you choose the nickel here, you still got the same 4 choices, but now you're doing it for 73. So it's recursive, right? You calculate how many ways are there to do 78. How many ways are there to do, so I asked 79 cents. How many ways are there to do 78? How many ways are there to do 74? How many ways are there to do 69? Go away. And how many ways are there to do, let's see, 54, right? And you add all of those. It's recursive. You do it on 70, you see how many ways there are for 78 by running the same function. Then you add it to how many ways there are for 74 by doing the same function, and so forth. These branching problems are ones that are classically done with recursion. Study Cracking the Coding interviews, study other things. Recursion is definitely more than like a one morning topic if you want to get more into depth with it. Okay. Thanks, everybody. Steph. Yeah.